So again, welcome to everyone who's signed on so far. We'll get started here in just a minute or two. Great. All right, well, let's get started, Tony and David. So good morning, everyone who has joined us. We appreciate you taking your lunch to spend with us. My name's Christopher Lee, and welcome to Decarbonizing Your Infrastructure, Planning for Electrification and Resilience. This session is going to put into context the current conversation the industry is having about carbon and identify the key components of a carbon action plan. We're going to review strategies to decarbonize new buildings, existing buildings, the electric grid, and transportation. And we're excited to have Anthony Gilbert from the Pratt Institute to discuss some of his organization's roadmap to decarbonize. So with me today, I have David Smith, Director of Energy Services with Burns Engineering, and Anthony Gilbert, Director of Administrative Sustainability with Pratt Institute, and myself. Again, I'm Christopher Lee, I'm Associate and Sustainability Coordinator with Jacobs Wiper Architects. So before we get started, I wanted to briefly introduce you all to our organizations. Jacobs Wiper is an architectural planning and interior design firm founded in 1981 by Terry Jacobs and Jamie Wiper. We're based in Philadelphia with offices in Raleigh, North Carolina. Our work has taken us both across the US and across the world with projects in Central America, Europe, Asia, as well as Australia. We've completed projects for clients across a wide span of sectors, from our addition to the Franklin Institute Science Museum to our dormitory at Swarthmore College. One thing that we're really proud of is that we're still working with some of the same clients today as when Jacobs Wiper started 3 decades ago. And I'd like to ask David to give an intro on Burns Engineering.
Thanks, Chris. Yes, hello, everyone. Thanks for participating in today's webinar. I'm David Smith, Director of Energy Services for Burns Engineering. And Burns is a full-service engineering and construction support firm based in Philadelphia. We've been in business for 60 years, and we have offices throughout the country with over 200 technical staff providing mechanical, electrical, plumbing, fire safety, and structural engineering. We also provide specialty engineering and design related to information technology, smart infrastructure, advanced security systems, and resilient low-carbon energy systems. Our markets are higher education, energy and utilities, healthcare, aviation, and railroad and transit. Excuse me. A focus at Burns is providing energy and advanced power advisory, planning and engineering services. We do this work for a wide range of clients, from colleges and universities to military bases and hospitals. Our clients, as different as they all are interested in lowering their energy costs, clean energy generation, or reducing carbon, or some combination of the above. A lot of our work also includes increasing power reliability and resilience, and we've been involved in more than 20 different microgrid projects of one kind or another, including the largest in the world for New Jersey Transit. Much of it starts with energy and utility master planning, where we try to develop a roadmap where we can look not only at the technical aspects of a project and how a plan comes together, but also involves extensive financial modeling, scenario analysis, and evaluating alternative financing and ownership structures. So with that, I'll ask Tony to give his greetings.
Good afternoon, everyone. I'm Tony Gelber with Pratt Institute in Brooklyn, New York. So we're one of the top art design and architecture schools in the world, and very proud to be working for Pratt for many years. We have a beautiful 25-acre campus in Brooklyn and a little campus in Manhattan. Unfortunately, we don't have too many visitors at the moment. So we're trying to figure out how to get to carbon neutral, and we have a roadmap, which I'm going to tell you about later. I'm also going to talk to you about how we're thinking of dealing with this COVID problem longer term. So talk to you later.
Great. Thanks, Tony. And with that, we'll jump right in. So there's three important ideas that came to mind when planning for and implementing decarbonization strategies, which are scale, infrastructure, and influence. Scale can give organizations and owners access to a broader range of options to decarbonize. Decarbonization strategies at the whole building level or campus scale can often have shared impacts and provide shared resources across multiple buildings. Infrastructure. Decarbonizing our infrastructure will take time, planning, and a phased approach. Organizations that have control over their infrastructure and building design standards can leverage this to set targets and requirements related to carbon, while also looking for opportunities to increase their resilience. And influence. Our companies and universities have always been integral parts of our local and regional economies. So actions taken by leading organizations can help spur transformation beyond their boundaries. And there is urgency for all of us to take action on carbon now. 2030 is only a decade away, and what we do over the next 10 years will define us and also determine the severity of the impacts of climate change that we'll face in the future. There's also urgency for us to scale up our efforts. Each year for the last decade, the UN Environmental Program Emissions Gap Report has compared where greenhouse gases are against where they should be to avoid the worst impacts of climate change. Each year, the report has found that the world is not doing enough. The Emission Gap Report for 2019, which this graph is from, shows that even if all the unconditional, nationally determined contributions under the Paris Agreement are implemented, we're still on course for a 3.2 degrees C temperature rise. Regionally, sea level rise is something that we're going to have to deal with if we stay on our current course. The study, The Rising Seas and Changing Coastal Storms, was commissioned by the New Jersey Department of Environment and prepared by Rutgers University and other leading climate change experts. The report concluded that the sea level rise projections in New Jersey are more than 2 times the global average, according to NJDEP. Sea level rise in New Jersey could rise from 2000 levels by as much as 1.1 feet by 2030, up to 6.3 feet by 2100, according to the study. Sea level rise is also a big global problem. In February of this year, the coldest place on our planet, Antarctica, set a new record high temperature of 64.9 degrees. Rising seas is also a problem that communities in Fiji are already dealing with. Communities are being relocated because of seawater is coming up to the ground, making farming and other daily simple tasks difficult or impossible. And the pandemic has made even more clear our impact on the environment. In Delhi, India, where the air is normally choking, levels of PM 2.5 and the harmful gas nitrogen dioxide fell by more than 70%, which is very clear from this before and after image. Regionally, the data indicates that the nitrogen dioxide levels in March 2020 are about 30% lower on average across the region of the I-95 corridor from Washington, D.C. to Boston, when compared to the March mean of 2015 to 2019. There are, though, several leading organizations that are working to decarbonize our buildings in part and in whole, and here are a few of the standouts. The Carbon Leadership Forum at the University of Washington is working to accelerate transformation of the building sector to radically reduce and ultimately eliminate embodied carbon from buildings, materials, and construction. Architecture 2030, whose mission is to rapidly transform the global built environment from a major contributor of greenhouse gases to a central part of the solution for the climate crisis. And 2030 districts, which were established as a global network of high-performance building districts and cities. Each district commits to meeting a 50% reduction in energy, water, and transportation related to emissions as established by the Architecture 2030 Challenge. And to illustrate the effectiveness of the efforts, this is a snippet from the 2019 annual report of the Philadelphia 2030 district that is made up of 47 individual properties representing 21.9 million square feet. And they've made some amazing progress in 2019, their second year. Close to 70,000 metric tons of carbon dioxide were avoided, and the participants saw a $17.3 million cost savings that was across the district. And legislation on carbon is also starting to be enacted. On May 18th, 2019, the City of New York enacted Local Law 97, one of the most ambitious climate legislations for buildings enacted by a city. The new law places buildings greater than 25,000 square feet on the path to meet the city's global goal to reduce overall carbon emissions by 80% by 2050 by setting increasingly stringent limits on emissions per square foot in 2024 and 2030. And the financial industry is also beginning to take action. The managing director of the International Monetary Fund has noted a range of measures they will take to prioritize climate change during her 5-year term. This includes supporting policies that require investors to disclose climate vulnerabilities, measuring a country's financial situation in part by its preparation for climate change, and pushing for countries to implement a carbon tax. And BlackRock, the world's largest asset manager, is also paying attention to climate change. The founder and CEO, Larry Fink, made the announcement in his 2020 annual letter to clients and chief executives. He said that BlackRock will exit investments that present a high sustainability-related risk. He said the company would also launch new investment products that screen for fossil fuels. So when we talk about carbon, there's 3 types of emission scopes that we should be aware of when we're targeting decarbonization strategies. The first is scope 1, which are direct greenhouse gas emissions that occur from sources that are owned or controlled by an organization. These are your boilers, your furnaces, the vehicles that your organization owns. Scope 2 emissions. These are greenhouse gas emissions from the generation of purchased electricity, heat, or steam. These are your off-campus utilities. And scope 3 emissions. These are greenhouse gas emissions from activities of the organization that occur from sources not owned or controlled by the organization, such as air travel, purchased goods and services that your vendors may provide, as well as your employee community. And with that context, I'd like to pass it over to David Smith with Burns Engineering.
Thanks, Chris. So I'll be talking about campus and infrastructure electrification. Part of that will be a discussion on transportation. Next slide. So what we're focused in on is the decarbonization of campuses and infrastructure, including transportation. And it's important as we talk about this to recognize how efforts to reduce carbon are part of and enabled by other key major trends. Specifically, what's happening now is renewable energy at large scale in particular is bringing down the cost of green power, and dramatically so in some places of the country. When coupled with battery storage, this is truly a game changer in terms of what type of power gets onto the grid and is available for purchase. Second is whether to power bus fleets or heat college dorms or power laboratories. We're confronted with the prospect of power outages and what those mean, even for a short duration, and the kinds of risks that are now presented by a fully or mostly electric infrastructure. So the upshot is enhanced power reliability and resilience become more critical, adding to already growing threats from extreme weather events. And lastly, alternative business models that leverage abundant private capital can enable and are enabling an accelerated transition to low carbon. So those are the main sort of trends that are setting us up for this transition that that's underway. Next slide. So fully electrifying campuses and weaning off fossil fuels entirely is, to say the least, challenging. The first order of business, though, should be to procure this increasingly cheap green power for your existing electric loads, lights, chillers, motors, computers, laboratories, plug loads. The second order of business is where it gets a little tougher, and that's with building heating. How do you heat a building electrically? While admittedly hard to do, if you're to do it at all, you have to commit to long-term planning. That includes ongoing reassessments as things invariably change and create new solutions and challenges. Here I'm referring to a range of technology disruptions and new regulations, laws, evolving financial incentives, potential penalties in the form of new taxes. And finally, an infrastructure transition of this magnitude is going to cost money. Potentially lots of it, but much of the existing infrastructure needs to be rebuilt anyway. So it's really becomes a choice at some point between business as usual or going down another path. Next slide. So I said renewable power is getting cheaper, particularly at scale, with large wind farms and solar farms that feed directly into the transmission grid. Well, within the last few months, a new record low price has been set for grid scale renewable power, and that's 1.7 cents per kilowatt hour, and that's through the Southwest Tri-State Energy Cooperative. It's pretty remarkable when you compare it to the cost of wholesale power presently in much of the country. It's probably in the order of 50% lower than the average. And it has particular implications for retail prices for large power consumers and like campuses or industry. So this downward trend in green power costs is being seized on by some universities who are opting to build large-scale solar farms offsite and lock into direct power procurement agreements over 20 or 30 years. So the likes of Stanford, Swarthmore, but it's not limited to higher ed. Cities like Philadelphia and Cincinnati are going down this path. Cincinnati procured a 100 megawatt solar farm somewhere in the city, I'm not sure where. Philadelphia is having a 70 plus megawatt system built in Lancaster County. And recently a commuter agency serving southeastern PA, SEPTA, is going down this road with a 43 megawatt system that's being commissioned and built. There's always also the on-site solar option, which if feasible has unique benefits, still very much worth considering, but the advent of these off-site solar systems that are dedicated to a single off-taker is really starting to make it possible to buy 100% green power from at a competitive price. Next slide. So as I mentioned, the hard part comes when we're talking about fully electrifying and shifting away from fossil fuel-based building heating. When you consider the great majority, something like 95 or more % of commercial buildings and 75% of homes are fossil fuel heated, you start to get a sense of the magnitude of the challenge. Transitioning to electric heating will be long and challenging, but there are ways to plan and strategies that can help mitigate costs. And as I said at the outset, some options around private capital that can really be instrumental in accelerating the process. Next slide. So building heating is challenging. Building heating with steam is even more challenging, at least as compared to hot water or hot air. While steam has many advantages, it's energy intensive and almost always a function of fossil fuel combustion. Over time, systems invariably have problems, especially district energy systems, even the best maintained ones. There's loss of condensate water in a lot of cases. Water's expensive, expansion joints fail, sections start to leak, boilers are 50 or 60 years old. It's problematic on a number of fronts over time. So, and controlling steam at the end use point is also difficult. You can see the picture here is really illustrative of the familiar open window temperature control system. It's obviously quite an inefficient way, but an essential way in a lot of buildings. Many districts and central systems are approaching end of life. So the question is now, how do we get out of steam? Next slide. And into hot water. So getting out of steam and into hot water is one strategy, and it's being sort of picked up and run with on a number of different campuses. And the question might be, why hot water? The reason probably most central is that you can make hot water cost effectively with electricity, whereas steam heating is almost always fossil fuel based and hard to do electrically. So less energy generally means less carbon, and even zero carbon if you buy green power. Heat pumps are the technologies that are pretty dominant in this along this path. It's air and ground sourced and variable refrigerant flow. These are different technologies as opposed to electric resistance heating that provide the potential for both heating and cooling through one system, and in a way that's relatively cost effective. Again, Stanford is a notable success story here, having transitioned from their fossil fuel-based infrastructure entirely to electric. And Ball State has installed the world's largest geothermal, ground source geothermal system that I'm aware of. Next slide. So if we accept the fact that hot water-based heating using electricity is central to reducing space heating related carbon, the question that follows is, how do we get there, particularly if we're starting with steam systems and infrastructure, whether it's produced at either the building level or through a central plant and distributed throughout a thermal system, distribution system. This can bring to mind the old saying that if you don't know where you're going, any path will get you there. So as I led on at the outset, committing to a long-term plan and undertaking that with a vision is first and foremost a way to get yourself started. Number one on the list of any kind of plan, it should be making your buildings as energy efficient as possible and cost effective. And from a timing perspective, and you're talking 5, 10, 15 years in some cases, a long-term plan will identify incremental transition points in time that can be leveraged from a standpoint of infrastructure renewal. So, for example, there are transition points as infrastructure plants and systems age out or are plagued by excessive maintenance costs, or as buildings are renovated. Those will be opportunities to shift segments or parts of your system over to lower carbon options. So the idea is there, if you're going to spend the money to rebuild an old system, think about how that can fit into your plan to do it in a low carbon fashion. Next slide. When you undertake this path of electrifying your infrastructure, you've got to take into account in your energy and utility planning the impact on electric equipment and infrastructure. Probably not hard to see that your current system will likely become constrained as you add a bunch of electric load related to building heating or other just general uses. This can be significant depending on variables, not least including climate. So if you're in a northern climate, you're looking at a relatively increased amount of heating load that's going electric. Another critical issue raised in this imagined all-electric future is power reliability and resilience. It's one thing to lose power in the summer and having to do without air conditioning, but it's a next level problem if you're talking about surviving without heating during a protracted polar vortex. One of the other loads that is also growing, speaking of air conditioning, is use of campuses through summer programs, and even just in the shoulder season, the need to cool more and more space. That's adding to the growth of electric loads, as is the increasing penetration of electric vehicles. So all of this means increased capacity, reliability, and resilience need to be essential elements of any strategy to decarbonize. And this is where, as I'll start to explain, microgrids can make a difference. Next slide. Decarbonizing transportation. We're working in a number of different areas around fleet charging, and this is something that we're seeing grow as an option that is being explored. So shifting gears to, no pun intended, to decarbonizing transportation and fleets, you have buildings that have a relatively long-term time horizon, but cities and states are seeing the opportunity to expand their electric vehicles as a means to more quickly reach near-term carbon objectives. Specifically, fleet electrification carries considerable promise, and that's because with a lot of technologies in this space, costs are coming down and performance is going up. So for buses in particular, for example, buses can go further, and they're lighter, and they cost less and less. They're not as cheap as diesels, but they're getting there. And as with an electrified campus, an electrified fleet will require a beefed up electric infrastructure, and for the most part, depots have only a minimal electric load capacity. Also, planning and executing a transition to electric fleets requires considerable flexibility, good timing, and you've got to be careful about future-proofing your approach. Finally, power resilience and reliability, again, take on new importance. Even a short local outage overnight when most buses would be charging can really have an impact on the morning commute. So next slide. At Burns, we are developing strategies to accelerate the transition to fleet electrification while avoiding a business as usual approach. Business as usual when it comes to powering a fleet that is transitioning over 5 to 10 years or 15 years would be to simply try and secure new feeders or bigger substations or both to meet load growth over time. While this may be part of the answer, an alternative approach is to consider also deploying a combination of energy generation and storage resources to provide a value stack of benefits, including infrastructure flexibility, load management, cost containment, enhanced power reliability, and increased resilience. So imagine for a moment a bus depot that has solar PV on site, potentially has a canopy, uses battery storage to manage and shift loads. Dispatchable generation is in place to provide power surety during outage events. And all of this can operate independent of the grid when called upon. These hybrid energy assets could be deployed in a modular, scalable way, affording some flexibility. Again, future-proofing. You don't want to buy more than you need. And with all the things that are changing, it's hard to know what exactly a bus in 2028 is going to need for power. It's invariably going to be less than it needs right now based on technology trends. But you can also defer capital costs through this strategy. So this new energy infrastructure that we're envisioning and the assets associated with it can be owned by a third party. And that can have the benefit of removing all capital outlays required to create an electrified depot. Next slide. So we're not just imagining this. There's actually an example of a bus fleet that's transitioning in this very way. That's the Public Bus Authority in Montgomery County, Maryland. They're going from 4 to 70 electric buses over the next 10 years. And as part of that, they're developing what we're calling a hybrid energy resource recharging center, or HERC, microgrid. And that's going to enable resilience. It's going to give them low carbon purchased generated on site and future-proofed recharging flexibility. The third party, they're also envisioning a third party owning and operating these assets, and which has obvious advantages, particularly now with capital shortages happening and budgets being cut in all areas of the economy. Transit authorities are going to be under pressure. But probably the best way to summarize the advantage to this approach is that you create a public entity has the ability to create a capital expense, transition that, convert it really to an operating expense, and avoid all that capital. And the OPEX, the good news is the operating expense of an electric fleet is less than the operating expense of a diesel fossil fueled fleet. So transitioning from diesel to electric is going to be a net operating expense reduction. So getting there with third-party capital is one trick. Next slide. So we talked about microgrids. This is, as we see it, a key aspect of electrifying infrastructure and campuses and transportation, and how we are able to rethink the systems and equipment that underpin electrification. So the grid is shifting. It's going to a more decentralized topology, including microgrids that can meet growing loads and do so in a resilient, flexible, low-cost, low-carbon manner. And business as usual, just building out the existing grid is been demonstrated in lots of places to be suboptimal. In some places, you can't get the power. In certain areas, it's very congested, and there's not enough supply that's available for this kind of load growth. So deploying generation and storage close to the grid edge, that is close to the loads, has a lot of advantages. It enables smart, responsive systems. This extends to buildings and other loads that are part of this grid edge evolution. Electric energy markets are also emerging to incentivize all of this, and we fundamentally believe that resilience and low carbon are not only possible, it's being demonstrated, but they can also have a payback. Next slide. So I mentioned these innovative business models, and I'm close to wrapping up, but this is in some ways the punchline. Innovative business models have been around for quite some time, but they keep morphing a bit here and there on the edges. But it comes down to being there's an abundance of private capital. So you've got private equity, sovereign wealth funds, all manner of private investment that's available for these long. Some of the old tried and true strategies around ESCO performance contracts and power purchase agreements are sort of, as I said, evolving. And now we're seeing a different type of public-private partnership, one that just recently was implemented by Ohio State, where they got paid up to $1 billion plus upfront from a third party, where the third party is taking ownership of their assets, their energy infrastructure, and there's a 20 to 50-year financing program associated with that. So this is really about not only leveraging private expertise and other people's money, but it's also about shifting the risk associated with these fundamental transitions that we're talking about. Last slide. So decarbonizing and electrifying facilities and infrastructure and transportation is gaining momentum. There are some easy options in the near term, and that is buying green power from the grid, potentially from a solar farm dedicated to your load, virtually at least. And there's a long-term transition for all of this that requires planning, commitment, and capital and vision. You've got to be able to see that this is possible before you start going down this path. Resilience has got to be foundational to this to this transition, and resilience in well-configured, well-thought-out constructs can have a payback. If financing can really shift the onus off of public entities onto private capital, can accelerate and de-risk the transition and convert capital expense to operating expense. So with that, I'll turn it over to Tony Gelber and or is it you, Chris? I'm not sure I've got the right handoff here.
It's me, David. Yep. No problem. Great. Thank you, David, so much. That was great. I'm going to kind of transition and talk about the architectural considerations for decarbonizing and some of the key parts of a carbon action plan. So here are some of the key parts of any carbon action plan. First, stakeholders. Identify a diverse stakeholder group that represents the variety of organizational interests and perspectives. This could be the president of your organization, deans or provosts of your educational organization, your procurement team, your food service managers, your faculty, again, if you're in a higher education organization, employees, and measure. We want to understand how to quantify your scope 1, 2, and 3 emissions and start to establish a baseline for each if you haven't already established one. It's really difficult to manage what you don't measure. And set targets. With stakeholder group, discuss and set target reductions from baselines and timelines for reaching those targets. Identify potential actions, initiatives, and other areas of study for carbon reduction and improve resiliency within your organization. Tracking and reporting. With stakeholders and staff, create administrative and automatic reporting tools for tracking your progress. Identify review periods for status updates on your progress. Evaluate and adjust. Report progress at recurring internal review meetings. Reevaluate and adjust initiatives as required to meet your goals. If it's not working, change it. And finally, communicate and engage. Report progress yearly at minimum and identify areas of success and where you guys know you need to improve. Continue to engage your stakeholder group and invite additional members to that group to keep interest high and momentum. Architecturally, when we're planning for decarbonization, we think of tools, data, and defining resiliency. So for tools, you want to understand the tools available to your organization to affect change. These could be financial or procurement tools. These could be building and design standards, or they could be administrative tools such as a request for proposal or request for qualifications. Drawings and data. You can aggregate existing building drawings, infrastructure maps, building maps, individual building plans and documents. You'll need these for reference, feasibility studies, to overlay diagrammatic information on them, to communicate to your stakeholders, staff, what's working, what's not working, and where areas of improvement are needed. We all know that no one likes to look at spreadsheets. And define resilience for your campus so that decarbonization efforts can also support resiliency. What will the key drivers of resilience be for your organization? And in the midst of the pandemic, resiliency can really take on a whole new meaning. During this time, obviously we're all staying in touch with each other, but this could be an opportune time for those of you who are working from home or able to work from home, are gathering and organizing your data, strategizing about your long-term goals, like David had mentioned, and you're able to measure and benchmark your existing building performance now because many of us have access to our utility bills online. Moving on to strategies let's start with existing buildings. So some strategies include establishing or updating overall building standards around products, around energy modeling, around carbon modeling. An example of this could be setting a maximum embodied carbon for drywall used on all your projects. Next would be setting targets for renovations. We know that these happen more frequently than new construction. So again, setting requirements for the materials, energy modeling, or carbon modeling that would have to take place during those renovations. And retrofits. When performing a retrofit, consider upgrading infrastructure that can improve the overall project or building performance as part of that retrofit. And thinking about the operation and maintenance side, of course, it's crucial to keep buildings running efficiently and proper. And proper refrigerant management is a simple but really important task we can all be aware of because it does have a big carbon impact. Recommissioning or retro-commissioning of building systems to make sure that they're operating efficiently and as intended during the design. Evaluate purchasing policies and around your consumables to understand what you're actually using. Also taking a look at the waste streams coming out of your buildings. And finally, pursuing building certification that gives rigor and process to show measurable outcomes for these decarbonization efforts that we're speaking about. Shifting to new buildings, some of the operational considerations for decarbonizing are requiring energy benchmarking or setting a max energy use intensity for projects so that buildings perform similar building types. Energy and carbon modeling that starts early design process. Reevaluating design standards for operational carbon and consider setting efficiency or building performance minimum EUI benchmarks or reductions from those energy use intensities from those benchmarks. And then in requiring demonstration and training of the equipment as part of the project. One thing that we hear often from our clients is that they don't want systems that their facilities teams can't operate. By including this training as part of the cost of the project, facilities teams can be set up for success in operating the building when it's turned over to them. In the context of the current times, for new buildings, it's going to be, again, listening to our health experts, following best practices, developing safety plans specific to COVID-19, and looking at ASHRAE guidance as it becomes available to us. But again, we're all waiting to learn more about the exact recommendations for all of this, what will be our new normal. On the embodied carbon side, when we look for ways to reduce carbon, we want to focus on the building structure and envelope first, then work our way to the interior. The majority of the building's embodied carbon is contained in these two components, the structure and the envelope. So engaging the project structural engineer will be an important process to do. Again, reevaluating the design standards for embodied carbon, specifically looking at the building products that you're allowing in your projects. And finally, requiring or encouraging carbon modeling using either whole building modeling software like the Athena Impact Estimator for buildings, or more detailed software like the Embodied Carbon in Construction Calculator. This is an image from the Carbon Leadership's Forum that shows how the Embodied Carbon in Construction Calculator, or EC3 calculator, is supposed to work. The process begins with material quantities from a cost estimate or a building model getting inputted. These materials are then multiplied by the embodied carbon of the material using either specific information on that product. Also results and gives the design team and owner an understanding of the project's total estimated embodied carbon and identifies the hotspots for the design team. This allows the team to focus their efforts on the areas where they have the most impacts. And with that, I'd like to turn it over to Anthony Gelbert from Pratt Institute. Tony?
Thank you, Chris. So good afternoon, everyone. Chris, can you advance the slide, please? So I'm Tony Gelber. I work for Pratt Institute in Brooklyn, New York. I'm the Director of Admin Sustainability. So welcome, and Chris and Dave, thanks for putting this together. So I have to give a little caveat before we start here. People always say I'm kind of carbon obsessed. So now I have a new obsession, COVID. So you could say I'm CNC obsessed, carbon and COVID. And unfortunately, the two things seem to go diametrically in different directions from each other. And so we've been talking about this reducing carbon. Now you look at some of the initial recommendations for COVID and HVAC, it looks like the carbon footprint is going to go out the window. So So bear with me today as I go through this because I'm a bit obsessed. And I liked some of the things that both Chris and Dave said about the urgency, right? Because, you know, when you look at that picture on the left, and I guess I can show you there you go. So that glacier is gone, right? And that's not me. I mean, I probably would have had ice cubes over here trying to save that glacier, but I couldn't get up there. So anyway, I'm obsessed with this problem, right? And then I've been working at Pratt my whole life, and our plant was built around, our college was built in 1887, and then the plant we have, which is the main stack, was 1900. About 3 years ago, one of our main boilers is out of water, and so we put this rental thing in here. And so we have this crisis, right? So we've got a carbon crisis, we have an infrastructure crisis, and now we have a COVID crisis. So the next slide, please. So what I'm going to talk about today, I'm going to talk about some of the goals. So we saw this roadmap. How do we get to these low carbon mandates, right? And we have an owner's rep and our engineer, our owner's rep is Jim Olmsted, and Jeremy McDonald's our engineer. So thanks to them for some of the input they've given us. I want to talk about infrastructure, institute needs, right? So when we started this, it was air conditioning, power, resiliency, and Local Law 97, which I think you heard both Dave and Chris speak about, and then flexibility. Now we have this COVID thing and what that's going to do, right? Why a roadmap? What are the options? What were our analysis? What are the risks? And then some conclusions. Next. All right, so I said I'm carbon obsessed, right? So, you know, this is this graph of carbon, of what we're doing in the world. And if you go down here is where we want to be at about 200 and up around 450, 460. So we have global warming and carbon. Then we have this climate change nightmare, which we've been kind of taking precedent in the last probably 15 years. Next. And then we have Pratt, right? So this is our college, this is my world, right? We have that original plant, and we have this, we call it our kind of museum, right? Because our plant is the same plant that an Edison had in downtown on Pearl Street in Manhattan. Next, Chris. So here we have three museum type steam engines, right? 75 kW DC, which we run about an hour every year to generate some lights. And that's the flywheel. But this is a museum. Next. And, you know, COVID-19, is yesterday's college education a dinosaur, right? So, you know, here we've got these dinosaurs and they see this COVID thing and, you know, I don't know, what should we do with the kids? Go back to school? Will they be safe? What happens, you know? So this is a big problem, and colleges are facing, prior to this, there were colleges facing a lot of financial exigencies. Pratt has been doing very well, thank goodness, but as we go forward between fighting with the carbon and the infrastructure, and now this COVID thing, it's going to be a struggle for everybody. And I like Dave there putting the cursor over his head there. See that, Dave? And some of these business models, I think these newer business models can help us with financing and operational costs. Next. And so, you know, what's this dinosaur education to me? Is it really going to change, or is in a year going to go back to normal? So that we know, but here, right if you look at the social distancing, you know, we're going to say, okay, do we have to reduce the number of students on campus? Do we have to increase the physical space for less students or more students? What do we do with the infrastructure? What do we do with the HVAC? There's now a whole kind of discussion and controversy over this whole lighting. Like, we're getting ready to redo the campus lighting, but should we be putting UVC in there? And I don't know what else is out there. Next. I spoke about this pretty much, and I'm just going to kind of recap. We need a new central plant and distribution. We need something to give us HVAC and power going forward. And Dave gave some good suggestions, I think. Our campus needs probably a 1,000 square feet? No, 1 million square feet. I missed a few zeros there. 1 million square feet in conditioning, right? Our electrical power, you know, some of it's still based on that DC wiring, not much, but some. And then our resiliency. So these are some of our needs. When you talk urgency, this Local Law 97 to our heads, right? Because there are three time periods, which I don't have on here, but 2024, 2029, and then 2034. And you're looking at 45, 65, and probably 80 to 85% reductions in carbon. Now, 2024 is 4 years away. So talk about urgent, right? And we're looking at that metric-wise. Can we look at the campus as a whole? Do we have to go building by building? So this is a very new law. Everyone's trying to figure it out. And then how do we pay for everything? Next. Let's pass this one. Oh, no, go back. I'm sorry. I thought I had repeated. So, right, so what are these COVID-19 implications? Well, on our infrastructure. So we had come up with a central plant, a smaller central plant, an air source VRF. And one of the main questions that I have right now is the recommendations that we made 2-3 months ago. Are those recommendations still valid, right? What do our institute need? So I had said we needed air conditioning, we needed better power. But what about this COVID thing? This could, if we have to change all of our HVAC systems, we could be spending millions on that. So I think our priorities may change. Local Law 97, you know, they may hopefully give us some leeway because of this thing, but I don't know. Space we talked about, and then this we talked about. So next. So when we had started this, we have talked about a failing steam panel, air conditioning, carbon caps, right, resiliency. And the thought was, do we do a kind of a seat of the pants approach, or we do some kind of a holistic pathway? So we came up with this roadmap intent. Next. And you know, that's part of our beautiful campus. So come visit us when you get a minute. Hopefully I'll be back there soon and I can give you a tour. But NYSERDA, which is a great place for resources in the state, gave us a grant. And then we put out an RFP. We had 9 firms. We selected Guth Consul out of Troy. Then we did a lot of data collection, metering. We looked at a whole bunch of options and these recommendations. Next. Our roadmap had 5 fundamental tasks. Central plant and our district heating system. What do we do, right? ASHRAE level 2 audit of all buildings and systems, a climate action plan to comply with New York City and ASHE, which is the American Association of Sustainability in Higher Ed, guidelines and specifications. And Chris talked a little bit about this, but you know, 2024 and 2028, if you're designing stuff now, you have to get these guidelines and specs right in your architects and engineers and planners' hands and tell them that these specs have to meet these goals, because by the time that space is renovated, you're at almost 2024. And so if you don't get this right now, comes 2024 and 2029, the penalties are huge, and you'll see that in another slide. So we had the central plant, the ASHRAE audit, we have the climate action plan, these guidelines, then how do we implement in funding? So those are the 5 tasks. Next. And this is our core campus. We have a couple of North Campus and South Campus and Manhattan Campus, but our steam plant is here. And this is, our steam plant feeds about 1 million square feet with high pressure steam. Next. And this was before Local Law 97. This was my graph to say, okay, how do we get down there? And Local Law 97 is probably a bit more stringent. But as you look at this decrease in energy and carbon, it's you know, it's graphically significant, and it's physically and financially significant. Next. So if you look at this Local Law 97, this is the real driver. And I mean, without this law, I think we would, you know, you can talk and talk, and voluntary stuff is voluntary stuff. But if you look at these years as we go, and I've mentioned 2024, 2029, 2034, and 2039, these are kind of the targets on carbon reductions. This is the carbon budget you get, right? So right now, that's our carbon budget for 2024. We think we're pretty good shape because we have been reducing. At one point, we were up to about a 30% reduction before that main boiler plant crapped out. And so what's the fine going to be, right? Well, New York City has assessed the fine at $268 a metric ton. I think it's a metric ton. It's very confusing, these tons and metric tons. I usually do metric tons. At any rate, you go to 2029, which is the year that the 2030 fine is based on. And it looks like we're in the range of $1.6 million per year. And I've talked to some of my colleagues in the hospital industry and the college industry, and we're all looking at these types of numbers, right? And then if you don't do anything by 2030, 34, you're up to almost 2 million. And, so this just gets worse and worse. A couple of things are out there that might be helpful. And one is buying either RECs, renewable energy credits and carbon credits, or a PPA, as David talked about. One of the problems here is that New York City is restricted by the J grid. And so it's not going to be cheap for us to get solar right into the J grid, I don't think. Dave did talk about solar on site, so we might be able to get a megawatt or 2 megawatts us cover. But this is a challenge. Next. So there were some fundamental questions that came up during this process, and again, they were mentioned before, but like steam or no steam, right? Centralized, decentralized cluster, air-cooled, water-cooled, right? So these are fundamental questions you need to look at, right? Air-cooled or water-cooled, right? So if we're looking at this variable flow, variable VRF, variable refrigerant flow, and then, or you look at a heat pump or you look at a boiler, you can go from COPs of like 0.8 to like 4 or 5 or 7. So this makes a big difference, right? Boilers or no boilers. This local law 97 is an electrification law, but can you get there, right? Because we have almost all those buildings you saw on the main campus are direct steam, right? So for us to convert from steam to hot water, as Mr. Dave recommends, Dave, you got the money for that? Don't answer. It's expensive and it's intrusive, right? At any rate, can we do, when you talk about change, can you do an incremental change that will wind up being transformative? I think you can if you plan it right. And then this urgency of all electric in 9 years, I mean, it's just mind-boggling. Next. So this is, what was this one? Oh, so how big and bad? Our plan is in bad shape, right? Move on. Next, Chris. And, I love these boilers. I have my New York City high pressure boiler operator's license, and there's a Cope's Volcan steam regulator up there, feed water regulator that nobody even knows how it works. We have steam pumps. We got a gem down here, but it's a gem. Next. Okay, so we did this analysis, right? We have a bad central plant, right? So we did a 20-year life cycle cost assessment. We had like 17 permutations of this thing, options up to kazoo. And then as we looked at the 20, we said, well, we should probably be looking at 30. So we went and did 30-year. Next. We looked at a centralized system, right? A new steam plant, a new hydronic plant, or a new ground source geothermal system. We did look at the microgrid, right? And CHP. And then we looked at decentralized, from individual building systems to cluster buildings. And we're probably at this cluster hybrid concept. Next. So I'm not going to go through each of these options. If we have time and you want me to go through it later or have questions, but go ahead, Chris, please. Keep going. Next. Okay, just want to talk briefly about technology, right? And this 97 is an electrification law, but for us to go from steam to hydronic to electric, Dave said that heating is a challenge. Electrically, it costs us 5 times as much to heat with electric. Now, if we go down to very good heat pumps, and we can go down to probably 2.5 times. We looked at the CHP systems, and some of these are right. I like CHP systems, but in general, the state and the city are looking to get away from fossil fuels, and so, this is kind of a conflict between the microgrid and the CHP. Chillers, I would rather go with heat pump chillers, right? So you have lots of different types of equipment here. And like I said, these COPs are all over the map. And so when you look at all of this, it's a very confusing and challenging task to figure out what's the best option. Next. Yes, so we're looking right now at air source VRFs, and they're flexible, they're modular, they take care smaller spaces. The real question is, are they good for COVID? And what's going to happen with the refrigerants? So there's some risk here. Next. All right, so we looked at, like, these are some of the plants we looked at, right? And there's what do we do? Heating plant, what was the capital life cycle cost, the payback, and the carbon reduction. So we started with like a 2,500 ton water-cooled chiller on a smaller central plant. This was a similar one. Then we did a geothermal, and then we did a larger geothermal, and then we added CHP, blah, blah, blah. We wound up with this low air, that should be an S, air source VRF. We looked at this new low pressure steam boiler with an air source VRF. We're looking at about $20 million of capital. The life cycle cost came out to $66,000 a year compared to these others, right? About a 30-year payback and about a 25 to 30%. I think this is a little low on carbon, right? And then if we go this route, as Dave said, you got to boost up your electric. So probably 5 to 10 million on electric. So you're looking at a $30 million project at a minimum. Next. And when you look at these life cycle components, you know, this was, I don't know, this graph's a little beyond me, quite frankly, but you know, you got the fuel, you got air conditioning, you got heat, I don't know. This was the winner. Next. The other thing we did was we put this matrix together, right, to say, okay, how intrusive is this project going to be? So we looked at the life cycle cost, the capital cost, the carbon cost, how difficult to update it, and then we ranked everything, right? And so we looked at this 3B1B is the one we chose. This came out to be like the best in this matrix. So I'm not saying this matrix works for you, but a matrix like this can help you make a decision. Next. So what's the ideal system for Pratt? Well, minimize capital and operating costs, meet local law 97, flexible, right? Minimize these risks. Next. So one of the things I said was we have this steam plant with steam infrastructure. And to move to hydronic is expensive, intrusive, right? Thank goodness Cleaver Brooks makes this boiler, right, in different sizes. This can be a low pressure steam boiler. It comes piped for hydronic, right? So we can throw that in right now as a low pressure steam boiler. And then as we go down the road in 5 years, if we want to go to hydronic, we don't have to redo the central plant. So when I found this, and other in the city is starting to use this also, it was like, wow, this looks like a savior. Next. So this is kind of a summary of where we are, right? So the low pressure steam plant, carbon, capital, and we had some other parts of the project, right? So we talked about backup generators in some of our spots for about 5 million. And then that whole task 2, which is the energy conservation, we need to spend about $10 million to get about a 10 to 15%. Talked a little bit of solar, possibly a PPA. When you look at all of that, you're only getting to about 40 or 50% down in carbon. So you're not there yet. So go, I think the next slide. Let me see the next slide, please. No, go back, I'm sorry. So how do we get to this 80%, right? So this electrical infrastructure, we're thinking we need to redo that. All right, next slide now. And how do we do this, right? So we can just delay, and then do everything. We could do several projects every year. We could do a project and wait, but this is the goal now. So how you do this is really up to you and your capital and how intrusive it is, but you have to pick a method. Next. This is the campus. I'm running out of time, so let's just go forward a bit. This was some of our audit, the task 2. You know, we think we can save about 10 to 15. All save on energy. Next. So this was our energy conservation measures, right? So lighting and controls, HVAC controls, steam traps, pipe insulation, retrocommissioning. You heard a lot of this before. You know, $10 million, and we're going to get probably 10 to 15% reduction in carbon. Next. let's skip this one. Keep going, please. Okay, so this is saying, this is that local law 97 slide. So this is saying that we need to get to 80 or 85% in 2039, and I'm saying we're not getting there, right? So go ahead, next slide. So when we look at this slide to say, okay, the externalities, grid, greening the grid. So I think that this is really going to be able to help us, hopefully. Our governor has promised that by 2030, we'll have 70% 70% greener grid. So we do all of the stuff we talked about, and then in 2030, this is not a Pratt project, but if the grid is 50% greener, we'll get about another 25% reduction in carbon. And so that will get us to 75 or 80%. So I think with the things that we have on the table, plus a greener grid, we can get to 80% carbon reduction. Next. And this says it a little better, right? So that's our additional 25% from the grid. And then the question is, what happens with COVID-19? And this has really got me very, very concerned, excuse me. Because I want to show you the ASHRAE recommendations. Chris, go ahead. So the crystal ball is saying, okay, pre-COVID, I had some concerns, and you can see I don't have much hair left to lose. And now post-COVID, it's like, this is a nightmare. Next. So I said that, number of students, going to go down, lighting, all of this stuff. But the HVAC, I think, has the most impact. Next. So here at ASHRAE's fundamental, they have a white paper on it, it's a draft, but increase outside air to 100%, disable demand control ventilation. So this is basically saying, take your energy conservation, open the window as Dave showed you, throw it out the window, right? Improve filtration. Well, this is great. Does it take a little more fan horsepower? Yes, but probably in the scheme of things, not much. Keep systems running 24 hours a day, right? Okay, so we try to schedule things. We try to figure out when the kids are coming. Preheat an hour or two. No, let's just run it 24 hours a day. Oh, put more air, put more filtration in the room, right? Okay, so I'm going on and on here. Oh, bypass energy recovery ventilation, right? So this recommendation at the moment is saying, just forget about local law 97, just pay the fine, pay more money, right? I think this is very critical to protecting your occupants, our students, our faculty, our staff. I'm obsessed, right? I said I was obsessed with carbon and COVID. I'm obsessed with this thing because, I don't know, what do you do? Next. So I don't know what these fundamental answers are, right? So we're hoping to, in the next month, to say, okay, do our initial recommendations still hold through with COVID? I can't give you an answer right now, I'm sorry to say. The 9 years with local law 97, that 9 years is still ticking by, right? Next. So next steps, evaluate the roadmap in light of COVID. We're working on that. What's the path forward, right? Complete some other stuff. And then hopefully implement. Yeah, go ahead, Chris. So I think we need a new grid, right? I mean, Dave is saying that, I agree with him. I like this concept of third-party deboom, right? Design, build, own, operate, maintain, right? I think that's a good idea. Biofuels, I'm a biofuels guy, right? My brother owns a big farm. You can take those cows and use the rear end of them, right? Our air source VRF, one of the things I like about that is we keep our steam system, right? And so we can kind of phase out the fossil fuel if we want. I don't know, is that my list? I probably wanted to keep going. So all that's old is new again. This slide I love because this was an all-electric building award that started to be after, right, the 50s when electric was going to be free. Remember that? I'm old enough to remember that. So between the electric vehicles and the all-electric, we're going electric. We were going electric 50, 60 years ago. Next. Next. Oh, I missed one slide. Keep going, Chris. Go one more, and I'll go the other way. Next, keep going forward, please. Cut it out. Is that my last slide?
That's your last one, yep.
All right,
Do you
so,
want to finish up with some conclusions?
so my conclusion is, I think renewables are in. I think electrification is obviously in. I think you really need to go through a really detailed process to figure out what you're going to do. Don't do it by the seat of your pants. I think you need to let your CFO know that everything's going to cost more money, right? Capital costs, operating costs, right? Now, Dave is telling you that the costs of electric are going to go down, but we bid our electric every year, and this year what happened? The capacity charge went up by almost 3/4 of whole flat will go down because of better electric pricing. They hit us with a capacity charge. So do your homework. Good luck. I'm done.
Thank you, Tony. So before we get into the Q&A, I just wanted to briefly share with you some certifications and benchmarks that address decarbonization in the certification. So the first one is LEED v4's building operation and maintenance. Some of the carbon-related performance requirements are obviously the minimum and optimized energy performance thresholds, the commissioning of the systems, the requirements for renewable energy and carbon offsets if you pursue those credits, refrigerant management, and definitely the alternative transportation. Next certification is the International Living Future Institute's Zero Carbon certification. This is a third-party zero carbon certification that can be applied to new or existing buildings. Some of its performance requirements are 100% of the energy used by the project must be offset by new on or off-site renewable energy. Note that any fuel type for an existing building is accepted, are not allowed to use combustion-based fuel sources. Offsets, 100% of the embodied carbon emissions from construction materials must be offset. And there is actually a 1-year performance period that you have to gather your data, submit that data, and then a third-party auditor will come out and confirm that all the information is correct and that you've successfully achieved zero carbon for your project. And then lastly, the benchmarks. This is called the Zero Tool. It's a really useful resource. You can use it to compare a building's design or existing building's energy intensity. Again, it's EUI with similar building projects. So you can enter in your building's information and it'll benchmark those for you. It can also help you understand how a building achieved a certain EUI, if it was through certain energy conservation measures, on-site renewable energy, or green power purchases. And it can also help you set an energy use intensity for a project. So let's say you're starting a new building project or a retrofit project. This can help you benchmark to see where you should be compared to your peers. And with that, that's the end of the content. So I'd like to open it up for Q&A. And Abby, I think I'm happy to manage the questions, but just again, wanted to thank Tony and David for your time this afternoon. So the first question is for Dave. This is from, it says for Dave, he said electric heating is the only option for building heating, but isn't the combustion of electric and solar heating an option? Some of the first solar collectors were used for water heating. So it seems, wanted to understand the options for non-combustion heating.
Sure. And it's actually something that I think has promise, not necessarily on its own. Solar thermal heating for any kind of large commercial building, depending on the climate, can be problematic. But you can supplement heat pumps with solar assisted systems, and there are some high temperature solar systems that will get you the kind of heat you need in some buildings, but it's really it's hard to get the amount of solar thermal on a building or adjacent to a building that is that matches the thermal requirement, the heating requirement on a per square foot basis. So it's not out of the question. It's certainly got potential as an assist to heat pumps. on the heating side. And I think you know, I know Canada has had some experience deploying that type of hybrid technology, and I think it has potential elsewhere as well. Really depends on the site and the circumstance.
Great, thanks, Dave. And to our participants, just to let you know, if you do have a question, if you want to use the Link Central dropdown, there should be a Q&A icon that you can click on and type your question in, and we'll work to review it. Here I have that panel up on my computer here. Dave, another question for you. If loads go all electric, what is the environmental impact on upgrading transmission lines?
Another good question. Certainly transmission, especially for these large solar and wind farms and any kind of large central generation, requires significant transmission infrastructure. One of the advantages to distributed electric generation is that you avoid those transmission investments. But that notwithstanding, you still have the need potentially for corresponding investment in transmission infrastructure to support these large centralized utility scale systems. So it's a trade-off, and there's also resilience impacts. Look at what's happening in California with transmission lines that are vulnerable to fires. So all of this sort of points in the direction of more generation being at the edge of the grid, close to the loads, less being centrally generated. But the promise and potential of renewables at scale sort of is a contradictory sort of driver that makes it something we have to just balance and accept as some of the trade-offs.
Great, thanks, Dave. A couple more questions for you too, Dave. What is Burns' experience decarbonizing district heating systems with hot water? Is it necessary to completely decentralize?
No, it's not. There are different configurations and solutions that have to do with satellite systems or some means by which you can optimize the distribution. But one of the challenges is if you are talking about a steam plant, then you may be able to maintain a central plant that's hot water based. This is what Stanford did, and accomplish a combination of central generation, but as with Stanford, they also decentralized and have local heating and cooling at some of the buildings or at satellites that then supply multiple buildings. So it's possible to look at different configurations and what makes the most sense for your particular campus.
Great, thanks again, Dave. A question came up for me. Chris, you mentioned coordinating with the structural engineer early in the project. What structural considerations can be taken in helping with decarbonization? The first piece is if you're using steel, just the quantity and amount of steel. So the structural system that you're employing is definitely important. So coordinating with your structural engineer to see, is it the right structural system to support your design loads? And is there a more efficient structural system you can use that has less tonnage of steel to accomplish, your design goals? Also, taking a look at the amount of cement in your design mixes. A lot of the structural engineers that are dealing with decarbonization are looking at the total amount of cement that they're putting into their mix designs. Can you reduce the amount of cement and still achieve the strength that you need? So there's a lot of different things, but primarily it's reducing the amount of steel tonnage and looking at the amount of cement, which is the most carbon intensive piece of concrete in the actual mix design. And then another question for me that came up, is the zero carbon certification required by any agency, cities, and towns? Henry, I'm not aware of any zero carbon certifications beyond Local Law 97, which we were talking about, which is for the city of New York. But I'd be interested to do some research and find out if any other cities or agencies are requiring this. Another question for you, David. What is Bern's experience with fuel cell technology, and what are some of the limitations if you have experience with them?
Sure, I do. We do. Fuel cells are relatively low emissions. They're not, unless they're fueled with hydrogen, there will be some emissions. And the advantages are that they will run typically in a base-loaded configuration, an operating mode, which is to say that they run steady constantly without turning up and down. Most fuel cells are constrained and cannot ramp up or down, so they're not good for load following, which calls into question their value in a microgrid when you have loads that are going up and down, and you have to have an asset that can adjust accordingly. They're also expensive, and the EPA, DOE just released a study on future cost of fuel cells and performance, and it's not as encouraging as I might have hoped. They're maxing out at 60% electrical efficiency, which is not bad, but and heat recovery of 20-30%. So in that respect, they look like cogen systems. Some fuel cells cannot are not designed to provide waste heat for beneficial use. We were part of a project for Kings County Hospital where 3.1 megawatts of actually a total of closer to 4.9 were deployed. 4.9 megawatts of Bloom fuel cells were deployed to limit the load growth on the Brownsville substation. And there again, it's a technology that's not really well designed for microgrid operation, but can be a source of heating and cooling, or at least heating and electric in certain applications. And it's it also has a low value of heat. You cannot get very high temperatures off of certain chemistries in fuel cells. Some are better than others.
Sure. For Tony, will permanent and or will these be temporary and reversible once a vaccine is available? Do you have thoughts on that?
Yeah, we're not sure right now. Number one, you always have to abide by whatever the local regulations and then the ASHRAE regulations. So as you're doing design, you need to take that into consideration. We're not really, we're trying to say how can we get our campus as safe as we can right now, and then what do we have to do in the next 6 to 8 months, say, to, do we change stuff? Do we just add better filters? So do we do stuff holistically or kind of piecemeal? So we don't really know yet.
Thanks, Tony. Another question. My understanding was that Tony mentioned that combined heat and power conflicts with the philosophy behind microgrids due to the use of fossil fuels. Dave, what are your thoughts on combination of CHP and microgrids on campuses?
Well, in the circumstance where there's not a carbon goal or constraints, CHP is a really good technology to provide resilience and microgrid operating capabilities on campuses. The microgrids for campuses make a lot of sense. And CHP, because of the significant heating and cooling loads that most campuses have, can be a great application. But as Tony mentioned, in the context of Local Law 97 and other laws that are coming about, as well as self-chosen goals and targets that colleges are signing up for or have signed up for, CHP is almost exclusively a fossil fuel technology. Again, fuel cells mostly run on methane or natural gas. So they too are not necessarily carbon-free by any means. So CHP and microgrids, fine, and really a good choice. But CHP and microgrids with a carbon goal is challenging. What we see instead are strategies to use a fossil fuel, to have a microgrid. Let me say it this way: to have a microgrid, you have to have a dispatchable resource. So you want to be resilient. You can only do that if you're in a position to push a button and have something start up that can power most or all of your loads, depending on what you've chosen as a structure or an operating scheme. So if you want to be a microgrid, operate on your own more than a very short period of time, where a battery might get you through, or some other non-fossil fuel resource, and I can't really think of any, but you would not be able to do that, operate as a microgrid for any length of time without something in the form of a dispatchable generator. So that's diesel or fossil or natural gas. But if you use it really in the context of a sort of a backup, an emergency resource, you can justify that. And backup generation is going to be here forever, as far as we can see. So you can deploy natural gas-fired assets as part of a microgrid. And if you have a carbon goal, you need to really limit the use of those to emergency situations. If you don't have a carbon goal, you can also use those resources in the markets and monetize and do load shifting and peak shaving in demand response programs.
Great, thanks, Dave. Tony, did you have any additional thoughts on combined heat and power?
I said I like combined heat and power, and I really agree 100% with Dave. I think it's a very good solution, except that when you have these very, very low carbon mandates, it's hard to run the CHP for any number of hours a year, and usually the payback is tied directly to how many hours a year you run. So there's 87, 60 hours per year. If you run it for half the year, that means you have to, your payback is probably twice as long, right? And so, from an emergency perspective, I like it. I think one of the things I do like about the DBOOM approach, right, design, build, own, operate, maintain, is that if you let a third-party operator run your microgrid and your CHP, they're not probably going to be they're going to be a power producer with probably some different carbon restrictions than the Pratt campus would have, and they would have to look at that. So yeah, I think it's a good technology. I mean, one of the things we started to look at was to say, okay, could we put in a small CHP plant and then run the electric for the heat pumps, right, or the air source VRFs from the CHP plant, right? Because that kind of makes sense. You take your CHP plant, use the heat as much as you can, right? Say 100% of the heat. So now your CHP plant is very efficient. You generate some excess electricity, and some of that electricity you use for the heat pumps. So we looked at that. And again, the capital cost came that the payback was not good. But I still think that that's a good concept. Dave, any thoughts on that? Have you looked at that?
Yeah, the combination of low carbon heating and cooling with a highly efficient CHP definitely can get your carbon footprint down. So it's clearly I agree 100%. It's one of the strategies, and you're right. If you've got a third party who's producing it, you may be less constrained, except for having to meet whatever your own carbon goals might be. So they may be at odds. But yes, I agree. CHP coupled with high efficiency HVAC and providing power and thermal to those resources is a great strategy.
Thank you.
Great. Thanks, Tony and Dave. So with that, I want to thank all our participants again for joining us. Thank you for your time this afternoon. Thank you for spending it with us. Dave and Tony, any closing thoughts before we sign off? Maybe Dave, you can start.
There was just a question about biomass, and I can take that offline, but
Oh, thank you.
yep. Thanks, everyone.
Thanks, Chris. Thanks, everybody.
All right. Thank you all. Have a good rest of your afternoon.